Everyone here? Yes? Okay, sweet. This is... Oh. We are starting. Okay, so this is our presentation on electrical discharge machining, EDM. My name is Luke McDevitt.
I'm Stanley Mugnelli.
And I'm JC Wardlaw. So a little bit of an introduction here. This diagram right here shows the basic machining process of EDM with your tool, your electrode, your dielectric fluid, and the work table down there. And the reason we chose EDM, or one of the reasons, is because, as you can see in this figure, the number of publications about EDM in the process has increased significantly in recent years. So we figured it was a good topic to address and present. So what we're going to go over today, closer, okay. We're going to talk about the processing principles, the different EDM types and components, efficiency and considerations, control strategies and future outlook, some applications, the results of EDM, and disadvantages of the process. So starting with the process principle, I'll talk about spark generation. So an electric potential is applied between the tool, also known as the electrode, and the workpiece. Both are submerged in dielectric fluid, which is commonly deionized water or oil. The energy breaks down the fluid and the plasma channel is formed, shown by the lightning bolt in the figure right there. And typically temperatures range between 6,000 and 12,000 degrees Celsius. So for the material removal, energy from the spark, it's going to melt and vaporize the workpiece, and a little crater is going to form. The tool also experiences wear, but it's relatively minimal and doesn't need to be replaced. The wear is not as significant as the workpiece and doesn't need to be replaced as often. Pulses can be repeated up to thousands of times per second, depending on the type of process that is being, or the workpiece that's being machined. And the dielectric fluid acts as an insulator for the when the energy is released. It cools the area, absorbs the heat, helps prevent any thermal damages, and it also flushes out the debris from the spark. And this video here is going to show like a general overview of EDM.
A small amount of material melts and vaporizes from the electrode and workpiece at the points of spark contact.
Guess the sound isn't working, but
a bubble composed of the gaseous
forms right there, the
byproduct
energy,
of vaporization expands outward from the spark channel. Once the pulse ends, the spark and heating action stop, collapsing the spark channel.
And the dielectric fluid,
dielectric fluid rushes into the gap, flushing molten material from both surfaces. This EDM residue consists of small solidified balls of material and gas bubbles.
Yep. So now, oh shoot, how does the EDM actually do this? So the electrode there's two different types of EDM generally. There's the die-sinking EDM, which is the kind that goes up and down, and then there's the wire EDM, where it continuously moves, it feeds wire. The feed of the wire is changed depending on whatever workpiece it is. So those are the two different types of electrode. You got the wire and you got the die-sinking EDM, which can be copper, can be graphite, or other composites. Then the motion and feed, so as we talked about, there's motors that pull the wire through, which allow it to cut both linearly, but also it can be angled and cut underhangs, which is unable to be done with a die-sinking EDM, because that just relies on linear actuators to move up and down. So both of them require a pulse generator, and that goes into kilohertz all the way, and the high-end machines are able to use megahertz for the pulses, so very, very quick pulses actually. And in terms of the dielectric fluid, that can be the oil, water, we talked about that previously, but it also needs some kind of system to continuously have that circulating and filtered. And then the controls, it's CNC controls and human-machine interface as per most of the non-traditional. So what actually changes the MRR, the material removal rate? So we got the electrode material, the workpiece material, the pulse frequency, and how long the discharges actually last. So those can be controlled via more efficient controls, but some things are pretty stuck, like the electrode materials. We haven't come out with many new ones, and the workpiece materials, obviously, that can't change. So how do you maximize the efficiency? You maximize the efficiency based on how well you control that gap and how well you control the fluid and the pulses. So some current control strategies, so we control the pulse generation, and you control the gap. But how do you do this? You do this with all different kinds of, there's servo actuated, there's linear motors, but something that's new is these piezo controls, which allow for both vibration in like the rotational axis along with just the up and down, which is really cool and allows for really, really, really precise holes. So that's kind of the future of EDM control, and we covered already the current situation.
So a lot of the inherent advantages of EDM make it a very desirable non-traditional manufacturing process in a lot of industries. This table highlights these industries and common applications of EDM within these industries. And you'll notice within each of these there's certain trends which stay consistent throughout each industry. The first one is that EDM is often used to machine hard or heat-resistant materials. Part of this is because EDM doesn't care about the hardness of the workpiece. It's a thermal process, so it uses very high heat to machine the part. For example, in the aerospace industry, a lot of times turbine blades are made out of nickel superalloys, which are very heat resistant. So EDM is a great process to machine these, which are otherwise very difficult to manufacture. Similarly, EDM is often used when you want high precision and want to control surface characteristics. For example, in the automotive industry, if you have a piston, you want it to be very smooth so that it slides smoothly within its housing. So you want it to be machined very precisely so it slides smoothly, and you also want it to have a very smooth surface to minimize the friction. And across all these industries, you'll see EDM is used when you're making a low volume of parts with high complexity and precision. You're not going to use EDM in a case where you're mass producing a certain part. So the advantages of EDM end up in these results. The first picture over here, it shows a uniform roughness on a titanium alloy used for a prosthetic implant. And so you see how it has like a micro dimpled texture, and that's actually very desirable for prosthetics because the human tissue can latch on to that surface and actually melds properly with the tissue. The picture in the middle highlights a microscopic gear which is machined to it. 500 micrometers, which is very precise. And this highlights how EDM is used in extreme precision industries. And a similar idea is shown in the third picture, where it's a zero tolerance EDM. And it's similar to the example we saw in class, where the cut is so precise that when you put the part back into the workpiece, you can barely even tell that there's a cut made. And despite all the advantages of EDM, it does come with inherent disadvantages. Because it's a thermal process that works with extremely high temperatures, there is the creation of a heat-affected zone around the gap where the crater is formed. This can have adverse effects on the workpiece if you don't want to have like unwanted cracks in the material, so you have to deal with those when you're machining. Also, there are environmental hazards. When you're dealing with the high temperature process that's essentially vaporizing material, you're going to have like smoke and vapors that go into the air. So you want to have good ventilation to deal with those. Also, since it is a high temperature, you're going to have fire and potentially even explosive hazards depending on how you set up your machine. And finally, when you do vaporize, the workpiece material is going to end up in the dielectric fluid. So you have to dispose of that slurry in an environmentally safe manner. All these disadvantages can be mitigated. It's just something you have to keep in mind while you're conducting the EDM process.
So after this presentation, we hope to establish that EDM is a non-traditional manufacturing process used to precisely machine parts with not only complex geometries, but hard materials as well, granting us both precision and control over surface characteristics, allowing us to achieve not only critical high-performance components, but these components that can't be achieved using traditional manufacturing or machining methods. Here we have two examples, again, of not only a medical application, but also a manufacturing application. There's a lot of advantages to using EDM, but there are still significant limitations. Continued research needs to be done with minimizing the heat-affected zones, improving the MRR further, and also finding a more environmentally friendly substitute for the dielectric fluid. With that being said, though, continued research and development will, with no doubt, cement EDM as not only a crucial manufacturing method, but one for further advanced applications in the future.
Yes, and now if you guys have any questions, feel free.
Yeah, can you go back to that zero tolerance thing for the gear?
Yeah. Oh,
That has to be like two parts that it made fit together, right? Not one part?
yeah. Well, the question was, is that two parts or one part that was made to fit together? That's actually just a part that it was one solid block of whatever material that was, and they just EDM'd it out, and then
Well, then how did they get the wire through?
they probably had like one of the edges, like a microscope. Oh, the question was, how did they get the wire through? They probably had like a small starter hole somewhere somewhere within that cutting process. Could have been on the back edge, somewhere back here where it's not in our plane of view. And then as soon as you have the starter hole, you can continue on with the rest of the cut.
Any other questions? I can run. Can I ask a question?
Yeah.
So the conclusion slide, I think you mentioned you saw the prosthetic pictures. Can you explain to me where actually EDM was used and then how, no, yeah, where are the parts, EDM machined parts, yeah.
It's this like wrapping right here with the like the complex geometry. It's hard for me to explain the manufacturing process. I should have included another picture for that, but I kind of wanted to just gloss over it. But it's like the parts that are supposed to wrap around the existing like bone.
Okay.
Yeah.
So maybe like inside was the
Yeah,
machine.
yeah, so-
then it's kind of covered.
Yeah.
Yeah. Okay. Okay. Thank you. Any other questions? I know this is team one, so you also a little bit nervous, but we still have time. No questions? Okay, then let's thank speaker. Yeah. Yeah, because no questions, Yeah. Anyway, thank you. Yeah. Okay, so again, team 2, please, or group 2, please prepare, your presentation. But again, the Excel file, please fill, the form whenever, you can. So if you have a computer, you can do right now. But the submission date is the end of the class, which is 23rd, So you can use two, yeah. You can do, yes. So you can do, so but if you do this, so when you receive questions, please, repeat the question, yeah, okay?
I think you go for. I think we're using this. Hello. Oh yeah, we're using this. And then I guess.
Does that one work too? Or? So they can use this one, and that one, and we use this one. Okay, so hi everyone. Today we present the non-traditional manufacturing method, fused deposition modeling with continuous fiber reinforced composites. So some background information on that. So when we speak of a polymer composite, there's typically a matrix material, which is a polymer, and then some reinforcement, which in this case with continuous fiber reinforcement are continuous fibers, as shown in the figure on the right. And traditionally, these polymer composites are made with thermoset matrices, which are polymer materials that cure in a chemical reaction leading to cross-linking between polymer chains and permanent cross-link. And this curing leads to limitations in joining, repairing, and recycling of these materials because they cannot be melted like thermoplastic polymers. And typically these processes require molds, which are, for example, hand layup processes or resin transfer molding. And unlike the traditional methods, there's this very common 3D printing method called fused deposition modeling, FDM, which is basically shown here on the right side, where a material is deposited layer by layer to create a three-dimensional part. And continuous fiber reinforcement can lead to a strong improvement of mechanical properties. So if these two are combined, continuous fiber reinforced composites in a fused deposition modeling process, that's a combination of additive manufacturing with the mechanical benefits of continuous fiber reinforcement. And that enables the production of lightweight, strong components while maintaining the design flexibility of the 3D printing process.
So, moving into the processing principle, as seen on the previous slide, CFRC FDM is an additive manufacturing process similar to 3D printing. A filament of matrix material is extruded through a nozzle, and a continuous fiber of reinforcing material is embedded in it. This embedding can occur within the nozzle, as in co-extrusion, to improve mechanical properties while enabling complex geometries, or the embedding can occur after the nozzle, as in dual extrusion, which optimizes part strength. A more detailed explanation of the equipment for this process will be offered in later slides. For now, we will look at the process parameters and their effects. The build orientation of a part, the fiber material, and the fiber volume content all influence part strength and the time required to print it. The increased printing temperature, slower printing speeds, greater infill density, and increased matrix filament feed rate all improve mechanical properties, as do triangular, hexagonal, and rectangular infill designs. And additionally, greater layer thicknesses reduce mechanical properties.
The matrix materials are usually plastics used in typical 3D printing operations like PEEK, PLA, ABS, PETG, nylon, things like that. The fiber materials are like carbon fiber, fiberglass, and Kevlar, which have a much higher strength and stiffness than the matrix materials, but also with a similar density, which allows the composite to maintain a similar weight. And then this picture on the right is a little misleading because the fiber volume concentration is usually much lower than depicted, especially in the case of dual extrusion, because it requires what's called a pre-impregnation step, where the fiber bundles are held together by a resin made of the matrix material, and the resin can be as high as 80% of the volume concentration. And all that goes through one nozzle, while in the other nozzle in dual extrusion is pure matrix material. In co-extrusion, the pre-impregnation step isn't as prevalent, so there's usually a higher concentration of fiber in this case. You can combine the different matrix and fiber materials to achieve desirable characteristics like resistances to wear and impact, and you can mitigate other concerns like warping and environmental concerns and cost and weight. Next slide, please. This is just a table of some common materials and their parameters, but for the sake of time, I think we'll skip that. Next slide, please. The equipment is mostly the same as typical 3D printing with the exception of the nozzle. In dual extrusion, you actually have two nozzles, one to extrude the fiber material and the other to extrude the matrix material. In co-extrusion, you still have one nozzle, but it's much more advanced and sophisticated than 3D printing because the materials have to be combined within the nozzle before they're extruded. But the process is mostly the same with you develop a CAD model in an STL file, and then using a slicer software, you develop a G-code, which is basically instructions for the 3D printer on how to make your part.
For this presentation, we will look at applications of CFRC FDM in the aerospace, automotive, and toolmaking industries. In aerospace, this process brings the benefit of being able to produce parts that reduce structural weight without compromising structural properties. This makes it an attractive option for producing drone and UAV wings, propellers, and frames. And an example of a frame can be seen in the bottom left of the figure. With respect to automobiles, CFRC FDM is useful for making functional parts and prototypes, such as side rear view mirrors on NASCAR race cars, and rear diffusers. The one interesting application of this process is how it can be used to recreate unique parts for classic vehicles that are no longer produced. By scanning a broken part, CFRC FDM can be used to print a prototype that can be fitted into the car's actual system. An example of this application can be seen in the bottom right of the figure. Apart from vehicles, this process, being able to make parts with intricate geometries that can be subjected to higher forces, is useful for making tools. Examples include drill templates that can be used for hand drilling holes on curved surfaces, and a contoured cutback tool that can be used for repairing turbines. These can be seen in the top row of the figure. That's it.
Okay, so even though there are many advantages regarding the design freedom and the mechanical properties compared to normal FDM process, there are certain limitations which mainly arise from weak bonding, damage, and defects. So weak interlayer bonding and weak bonding between fiber and matrix, so interlayer and intralayer bonding, are caused by insufficient wetting time during extrusion, and also a low printing head pressure, which is far lower than the pressures that can be reached in traditional processes. And damage of the fiber filaments is also a big problem, because as shown in the figure, the filament or the fiber is bent by 90 degrees as it's being deposited, and that leads to a reduction of 60% in stiffness and strength compared to the unprocessed fiber material. So the materials don't reach their full potential in this process, which leads to weaker mechanical properties compared to traditional methods. And yeah, defects are a big problem. They're shown in this figure and categorized into fiber defects in red and resin defects in blue. So for the fiber defects, things can be found like twisted fibers or fibers that buckle within the nozzle, broken fibers shown up there, wrinkled fibers or non-uniform distribution of fibers, and all of these lead to fibers not reaching their full reinforcement potential. So whenever they're misaligned or broken, it leads to a significant reduction in mechanical properties. And for the resin defects, there's warpage here shown on the left, because there's no mold and there are high temperatures involved. So yeah, the material tends to warp. There are layer steps, which are also common to see on the surface of a 3D printed part. And then there are 3 different kinds of pores, which are also highly problematic, because there can be like more than 10 volumetric percent of pores within the part. So intralaminar pores, and overlap pores, as shown on the right. And other limitations regarding geometry and accuracy. So the slicing software restricts fiber placements to certain areas of the part, so the user cannot choose where the reinforcement is placed completely freely. There's a lower accuracy compared to the molding processes, and I already showed the warpage on the slide before this. And there's a reduced reproducibility and reliability compared to molding processes, because there is no mold, and it's also not, the process is not as robust as traditional methods. And economically, there are also limitations, because it's a time-consuming process, and the filaments are typically costly, especially the fiber reinforced, the endless fiber filaments, and thus it is infeasible for large-scale production and suitable only for small batched or specialized applications.
The current advancements. So we're focusing on reducing the porosity and the other defects that Ben just talked about between the fiber matrix and the layers. 3D composite printing uses 2 methods, co- and dual extrusion methods. This improves the bending modulus by 28% and the strength modulus by 45%. This gives us a better first generation prototype. Using AI assisted design, we can find defects before in our G code before we print. And next slide. Just trying to get through this. Conclusion and outlook. FDM is an advanced to traditional composite manufacturing owing to its versatility, ease of use, and high design freedom, and no need for a mold, so it's much cheaper than producing something that you need to get a mold made. Limitations remain, including porosity, layer adhesion, and geometric constraints, also with the G-code and slicing, and also embedding the layers without defects. Future advancements in this area include improving fiber orientation and improving print head design, enhancing software tools, and advanced materials. And that's it, I think. That's our conclusion.
Okay, so any questions? Yep.
I guess my first question would be, what are some of the ways to like reduce some of those like errors in manufacturing, like the porosity or like broken fibers? Like, what are some of the ways to mitigate that?
There's the weight. Sorry, I didn't quite understand that.
What are some of the ways to like mitigate those errors in manufacturing, like the porosity or broken fibers?
Yeah, so one method that was just introduced here is the 3D compaction printing, where the core dual extrusion is followed by a presser roller application, so it's shown here on the right. Because, as I mentioned, there's an insufficient pressure in the, insufficient pressure in the printing head. So if depositing the material is followed by a pressure application with the compaction roller, that can lead to increased interlayer adhesion and reduces the porosity. So that's one method that researchers have been working on to improve the mechanical properties. Yes?
How does the strength compare to traditional carbon fiber layers and such?
It's a lot lower.
We showed the improving through the bending modulus and the strength.
Traditional fiber, not that traditional 3D printing.
Oh,
I don't think we had a number for that in here. But even, so yeah, this compaction printing, it improves the bending modulus by 28% and the strength by 45%, but it was still lower than, for example, a resin transfer molding process, because there the continuous fibers can just be laid in the mold and they don't get damaged at all. And then the wetting is also a lot better because there are higher pressures involved. So yes, the 3D printing process cannot reach these mechanical properties. Yeah. Yes.
I know in like a resin, was it called resin transfer molding process, the orientation of the fibers between layers of layups is like a really important consideration for the directionality of the part strength. Are there like similar considerations in this process in terms of like infill directionality?
Yeah, of course. So the fiber reaches its full potential if it's like loaded along the which is it? Like the one axis, if you want to say so. So yes, it highly depends on how the material is deposited. But that's also one limitation here, because I mentioned that the slicing software limits these like paths where the fibers can be deposited. But yes, it works similar, yeah.
I think it's almost time, so let's have speaker. So when you speak, please keep your microphone close to you. I know you are nervous, but not like that, like that, So now you feel, right? How I feel, So whenever you are ready, please, start.
Can you make sure on the video that the sound is turned on? Because I'm scared it'll be like really loud.
Okay, do you want me to? Oh. Yeah, I can do that. That's fine. Okay, introduce. Oh, no, that's fine. Okay, hello, we are Team 3. Welcome to our presentation on a comprehensive overview of water jet machining.
So for the outline, we're going to run through basically an introduction looking at the processing principles and equipment, different applications where water jet machining can be used, and then also discuss in general the advantages, disadvantages, and what's currently happening in the industry for water jet machining.
So first, I'd like to just kind of reintroduce the concept of how water jet machining kind of works on a really general level. And then we're going to take a look at a little video just to watch it happen for fun. So basically, the principle is that you're removing material via water, you're blasting the part with water, and it erodes away material. And then this has some distinct advantages because you're using water as a tool material. Water is clean, it's environmentally friendly, it's non-toxic to humans. And we'll explore more advantages of that as we go forward. And then it also has a wide variety of applications, both in the types of operations you can perform and in the materials that this process is applicable to. So before we start the video, this is one I took on campus recently in one of our labs, making a part for Dr. Greenslet's research lab. And you'll see two things. You'll first see the CNC control software working, and then you'll see the actual equipment running. So there's a little cursor that's showing what path is being traced, and then this is the equipment. It's moving a little slow to kind of see, but yeah. Also, the part is submerged in water during the process to prevent splashing. And then on the next slide, we can see that was the part when it was finished being machined.
Okay, now we're going to review the process principles and equipment for water jet machining. So as Jamie went over, the main material removal mode is the high velocity water jet. The erosive force of the high velocity water jet on the workpiece material. The equipment that allows this to happen is, first of all, a hydraulic pump that pushes water through the system. An intensifier, which is a double-acting hydraulic reciprocating pump that increases the pressure of the water to a pressure high enough to put that erosive force on the workpiece. An accumulator maintains the pressure of the water and makes sure there's no hiccups as it's moving through the system. Control valves and high-pressure tubing facilitate the movement of water from the accumulator to the nozzle. The nozzle is the tool that ejects the high-pressure water onto the workpiece. And as you can see here, there's various design parameters involved with the nozzle that can change your end result. And then most water jet machines use a CNC control system that is used to program the movement of the water jet head or even the movement of the table, like you can see in Figure 2 here. Okay, now I'm going to talk a little bit about different machining operations that water jet machining may be used for. Firstly, water jet machining can be used as a cutting operation. It is best suited for 2D geometry because of the nature of the water jet machinery. It may also be used for drilling, and this is a cool application because it requires no pilot holes in order to do so.
It may also be used for different finishing operations, surface finishing and cleaning. This may be done by reducing the water pressure so that it does not cut through the material, or maybe adding air in the water jet stream. And finally, it may also be used for deburring. The graphic on the right shows the water jet machine being used to deburr holes in a material. Often when it's used for deburring, anti-oxidation additives may be added to the jet stream to prevent rusting of your workpiece. So there are a number of the process parameters in your water jet machining process that can affect the end result of the workpiece that you produce. First of all, the workpiece material thickness and the hardness of the material may impact the effectiveness of your water jet machinery. This table on the right shows some different materials that may be cut by water jet machining and the thicknesses that they may be cut with. Additionally, the setup of your machine may impact the results that you have, including the feed rate of your jet stream, the water pressure, which is related to the velocity of the water jet stream, and the standoff distance, which is defined as the distance between your nozzle and your workpiece surface. Finally, we talked a little bit about the different nozzle types. The geometry, diameter, material of the nozzle may impact the results that you have in your workpiece. This other graphic on the right shows the same thickness of material cut at two different speeds. The one on the top has visible striations in the material because the feed rate was too quick, but then the one on the bottom was done a little bit slower and produces a more even, desirable surface. So the water jet machine operator should take careful consideration for their feed rate in order to produce desirable parts.
So looking at applications, due to water jet machining's versatility and just how well it can be used with different kinds of materials, it is used in a lot of industries. One of the most predominant places it's used is in cutting metals and composites. The aerospace industry specifically does use a lot of composites, and you'll see in Figure 5, this is an example of composite material that water jet machining can cut, and you'll see that the shape is actually very intricate. It's an intricate design, and it does leave a nice clean surface upon cutting. In addition, water jet machining is used a lot within food and agriculture. So when they're cutting soft meats, fruits and vegetables, more of the softer kinds of foods. Since water jet machining does work for both soft and hard materials, it can cut through meats. It's more often used though to cut soft meats. And in addition, a benefit of using water jet machining within food and agriculture is that there's no cross-contamination since it is water and the tool itself is not touching the food, for instance. So if anything, there would be cross-contamination from potentially if the similar bed was used for both a vegetable and meat. But since it's the water, there's no cross-contamination between different kinds of foods. In addition, water jet machining is used to cut PCBs, fiberglass, polymers, wood, paper, marble, different kinds of materials. And the speed and pressure of the water allows it to be able to cut through these different things with high precision, high accuracy, and with nice surface finish as well. In addition, it can also be used for organic material, so through machining bone, also in dental applications. With the bone, though, it does, you have to play around a little bit more with the pressure. There is something called a pulsating water jet machine as well. So it is still using water, but the kind of method of the water distribution can change a little bit, but it's still the entire water jet machining process. And you'll see in Figures 6 and 7, those are two examples of fruits being cut. You'll see the skin can be nicely cut off. There are precise cuts, and this is also good when these are then packaged and then shipped off to whichever store they're going to be sold in.
So just to kind of expand on the advantages of this process, again, it's a very environmentally friendly process just because you can filter and reuse the water. Water is a fairly abundant resource, and it's not going to spread toxins. Your material removed will accumulate, and you will have to dispose of it. I don't want to ignore that, but that's inherent to any material removal process, so you don't have any additional contaminants on top of that. Again, you get to avoid workpiece contamination between workpieces because the actual machine, like the nozzle, does not come into contact with the workpiece. And then you have a lot of advantages related to effects on the workpiece that exist in post after many other manufacturing processes. like a work-hardened layer or thermal defects, residual stress, things like that are avoided almost entirely in this process due to it not being as much of a like cutting, chip forming process, but rather an erosive process. And the water flow also, keeps your part cool and everything in the process as well. So yeah, and then also one final one just to kind of hammer on that is that this is one of the only processes that is like really good for cutting soft materials, like even really soft materials at a high processing rate and with good surface quality and stuff.
So with the advantages, there are also a few disadvantages. For instance, water jet machining can require additives for high quality cuts depending on material hardness. Like we said before, it is good for softer meats, but let's say you want to cut through something that's a lot thicker, something that's harder, you might need to add an abrasive in that sense. And so then typical water jet machining would not be the best choice for that cut, as the surface would not be as smooth, the cut itself would not be as precise and defined. In addition, it's not the best process to use for mass manufacturing due to the high cost of the actual machine itself. It can be very expensive. You can save money, especially since you're able to reuse water and it's environmentally friendly, but the actual machine itself does have a lot of cost with it. There's a large machine footprint, and there's also a high maintenance cost and hourly cost. So like I said, where you are able to save money, you also would have more spending depending on how long you would need to be producing something. So mass manufacturing, if you're trying to produce a lot of items really quickly, it might not be the best option to use for a non-traditional manufacturing method.
Okay, and then finally, improvements are being done to increase the quality of water jet machining results. For example, research is being done to increase the water pressure and thus the machining speed without negatively affecting your results like we saw in the process parameters section. And improvements are also being done to increase the complexity, such as the CNC control, allowing the CNC system to more efficiently nest parts, integration with other processes, combining water jet machining with abrasive water jet machining, allowing a user to turn that setting on and off, and improvements in nozzle geometries, such as you see in Figure 10. Okay, and in conclusion, water jet machining is a very viable machining method with a lot of different applications and minimal adverse effects on the workpiece. So it is environmentally friendly, cost-effective, and energy efficient, and very relevant in many industries. Thank you.
Hey, great presentation. I was curious for the food industry, how the machine is adapted to make that process doable. So I know traditionally it's like a basin of water with some kind of graded mesh that you can set your part on. Do you know if you're like cutting, say, meat and trying to, go through that process, how that machine looks?
There is, so at least like what we've seen in our research, it's more like a conveyor belt kind of style. So I don't know if you remember in class, like the way they were cutting celery, it's kind of a similar process for a lot of meats too, where it'll just pass through. You have the jet stationary in one area with the nozzle, and basically the meat will be passed through and it'll just precisely cut it as it's passing through. Does that answer your question?
Yes, it does. Okay. Thank you.
Any other question? Yes, Will.
So with the food cutting, can you still reuse water? That seems a little unsanitary.
It definitely depends on, I think, the, not the family of food, but like the kind of food you're using, but definitely no. Like for meats versus vegetables, you don't want to cross-contaminate in that sense. When we were talking about cross-contamination, it was more so like you can use the same water stream, but not necessarily reuse that water back into it. So it's just very dependent. It just depends on the food industry you are in, but yeah.
Any other questions? Good. You guys made me run. Which is good, No, it's good.
So I had a quick question. Like, as you mentioned, this is only for a 2D geometry. So like, is there a way to make a hybrid or model of it with water jet and a numerical control machine combined, and like some way control the depth of the water jet and create a 3D part out of it?
So it can be adapted for 3D machining. One of the primary ways that I've seen this done is through control of the angle of the nozzle. So by angling the nozzle and being able to control that throughout the machining process, you could create sort of like, I almost want to say like a 2.5D geometry, but it really is like 3D. And then also, I think one of our figures showed a deburring process integrated with like a CNC, I think it was a CNC milling machine. And I imagine that those type of applications could be done, but I don't know if you could achieve the exact like depth of cut as you could with, say, a mill, where you know, oh, I'm plunging the tool exactly, 10 millimeters below the part surface. I don't know if you could necessarily control that with a water jet, yeah.
Maybe one more question? Anyone? Can I ask one question? So then, looks like it's already established process. So what is the future work if you as a researcher, or is any researcher, or anybody say like what the future work needs to be done?
That's a great question.
Thank you.
Sure. Well, I think that the most common way that I have personally seen water jet machining, both like in my own research and in literature, is doing totally through cuts. So I think the biggest area for improvement is, as we talked a little bit about, like establishing different surface finish options by changing the nozzle geometries, even adding air into the stream as we see in the fuzzy jet. Yeah, I think there's a lot of area for improvement in surface effects.
Okay, thank you. So let's thank speaker. So I think day one, I think we can, you can go back. So I think day one, you all did good. So from next time, so maybe next three groups, please try to be, efficient between, kind of transition time. And then Excel sheet, that's the evaluation form. It's under form folder. So please fill out the form every time, And because then, it's just convenient and it's easy, right? So is there any questions? Yep. No, you do not have to evaluate your own presentation. Okay, this is on, so you can skip your team. Any other questions? So on-campus students, submission deadline is 23rd, midnight, 11:59. Okay? All right, thank you. So see you on Friday, right? Yep.